Savvas Marcou. Hey everyone, and I'll be introducing our speaker today. So Savvas Marcou is a fourth-year PhD student in the Berkeley Seismology Lab. He hails from a small island in the Eastern Mediterranean and came to Berkeley after 4 years in London in the UK, where he did undergraduate and master level study in geophysics. In his PhD research, he uses observation from the seismic stations and smartphone waveforms, as well as people, and applies data science techniques to learn more about earthquakes and the ground shaking they produce. He also uses data from the MyShake app, built and operated at UC Berkeley, to assess the performance of California's earthquake early warning system. He's also very passionate about communicating science to people of all ages, and is active in science policy and communication. When not looking at wiggles, he can be found carrying out culinary experiments, marveling at the Pacific Ocean, biking the Bay Trail, or hiking.
All right, thank you very much for that introduction. Hi, everyone. I'm Savvas, as we were introduced just now. So I'll be talking to you all about wiggles. But before we go to that, I was asked to give you a little bit of a spiel about where I came from. So we did that already a little bit, but I'll just reiterate that quite a little bit. So I was born here in the Eastern Mediterranean, a small country of less than 1 million people. So I spent the first 20 years of my life there. I went to high school. I did my army service there. So that's where the decision was made to go into geophysics. So how that decision was produced, I was in high school and I thought I would be a physicist. Like every budding physicist, I had read Stephen Hawking's brief history of time. And it was kind of like, okay, yeah, we'll do that. But then I discovered that physics is a lot of abstract mathematical concepts a lot of the time. So I did not want to do that. At the same time, I was doing geography. So I went to 2 geography Olympiads, first time that Cyprus was going to these competitions. So I kind of said, okay, maybe these phenomena that occur on the Earth are good to combine with physics. So that's how we landed on this geophysics. It was kind of a frontier for me. Nobody I knew did geophysics. So I just went and took a leap of faith, 2018 to 2022. I was in the UK at Imperial College, did bachelor's and master's in geophysics there. And then that's the first time I studied wiggles, also called earthquakes. So that's where the decision was made to fly across the Atlantic, across the continent, and land here in Berkeley, where I've been since 2022. I'm a PhD student in Earth and Planetary Science, but my research is done in the Berkeley Seismology Lab, where I study all things wiggles, as you will see in this talk. Okay, so let's jump into this. Many of you sitting here might be asking the question, what on earth does a seismologist do? So how many people here have heard the word seismologist before? Yeah, okay. So to you, this word might just mean someone who studies earthquakes, but I do want to simplify this a little bit more. So we're going to use one of my favorite goofy movies, Bean from 1997. This is Mr. Bean. In this movie, Mr. Bean is sent to Los Angeles to go to a gallery, and he says in his quote in the movie, I just sit and look at paintings. So this quote applies to me very simply. We just substitute a word. I just sit and look at wiggles for most of my time. So that's what a seismologist does. But why on earth do we look at wiggles? So here's why. We live on Earth. The Earth is vibrating all the time at all sorts of different frequencies across the frequency spectrum. So you can imagine that as the notes that the Earth plays all the time. And the things that produce vibrations are widely varied. We have the oceans produce vibrations, humans produce vibrations, cars produce vibrations, trains produce vibrations, ships produce vibrations. You get it. So all of these things that produce vibrations can be recorded, and all of these vibrations carry information about the things that produce these vibrations, as well as the path they took through the interior of the Earth. So people like me, seismologists, rely on a team of technicians to deploy seismometers, things that measure these vibrations. We put them out all over the Earth, and we get the data that we need to study these vibrations and make sense out of them. So in the last few years, we've made incredible progress in putting microphones into the ground. I just pulled this figure a few days ago. The number has climbed up to 15,000. As you can see, the yellow triangles that show the locations of the stations all around the globe are very heterogeneously distributed. We don't have that many all over most of the globe, We have perhaps too many. You can't say that as a scientist. You have a lot in the US, in Europe, parts of Central Asia, in Japan, up in Australia and New Zealand, the west coast of South America, but not that much in Africa, the center of Russia, or the oceans. And remember that the Earth is 70% ocean. So we're not there yet in terms of global coverage, but we are doing much, much better than what we had perhaps 30 years ago. So these are our microphones. These are recording what we need to get in terms of wiggles. But let's look at how we actually use information in wiggles. So the whole crux of this whole business, all of seismology, can be perhaps distilled to two things. You have a source, whether it is at the surface or deep underground, that produces energy that gets put into the ground in the form of seismic waves. These seismic waves have to travel through some portion of the Earth, whether that be a short path or a very tortuous journey that takes thousands of kilometers. And they will eventually reach one of our seismic stations and they will get recorded. And the wiggles that get recorded carry information about that source that produced them, whether that source is an earthquake, an explosion, water flowing, traffic, a whale in the ocean. They will carry information about that source. And they will also carry information about the path, the journey that they took through the Earth to reach our recording station. So seismology can be distilled to two things. If you want to study the structure, you want to build a model of the Earth's internal structure, you need to assume you know the source. If you want to study the source, you need to assume you know the structure, what structure the waves pass through. Now, of course, some of you might be sitting there thinking this is a bit of a chicken and egg problem, and it is. Seismologists have to make some assumptions about how much they know, and these two things kind of trade off together, so they are not perfectly known in any sort of circumstance. So this is where we are. But I am very happy to give you our first wiggle of this talk. And this is an earthquake wiggle. It was recorded 15 years ago now in March 2011. So it's next week, this anniversary of this magnitude 9.1 earthquake in Tohoku, Japan. It's one of the largest earthquakes ever recorded. So this is what the recording looked like here in Berkeley at station BKS, which is just above the stadium near the Botanical Garden. So this is a wiggle. So I just like to open it up to people in the audience to tell me, what do you see here? What does this wiggle look like? Any comments, ideas about the shape, the frequencies you see here, anything? Yeah. Yeah, so this kind of lasts a while, and it did last much longer. I did cut it at 60 minutes because I wanted to show you the interesting bits of it. So that's a good point. What else? What about the shape of it? Is it uniform throughout? Does it grow? Yeah.
Big, really suddenly and rapid.
Yeah, so that's a very good point. It has a very subtle beginning and then it grows quite a lot. So what I really want you to take away from this picture is that this wiggle, that we call a seismogram in seismological speak, really comes in three parts. So it has a first part, that is the free wave. That is a P wave because it's primary. It arrives first. It travels very fast. You can see it has quite a high frequency content, like very high pitched. If you were thinking of this in terms of music terms, then you get something called the S wave that arrives second. It is S for secondary, as you might have guessed. It is higher amplitude. It's stronger than the P wave. And it has even those lower frequencies, lower pitch. And then you have the third part that kind of continues quite a long time. It seems to decay exponentially. That is the surface waves. Surface waves result from when P waves and S waves kind of interact. They interfere, and then they get trapped near the surface of the Earth, and they just roll around, all around the surface of the Earth for hours and hours and hours. So this is what an earthquake wiggle looks like. Okay. Now, seismology started out because people found out in the 1960s that the big powers of the time, the US and the Soviet Union, could actually spy on each other and make sure that no one was cheating restrictions on nuclear testing regimes that they had agreed to at the time. So it turns out that the same way that earthquakes produce wiggles, explosions produce wiggles too. So I will give you another little quiz here. I've got two events that were recorded in 2017 in South Korea, station INCN in Incheon. So I've got these two pictures here. So one of them is an explosion, one of them is an earthquake. So based on what I showed you before, is there anyone who can hazard a guess as to which one is the explosion and which one is the earthquake? Any guesses here? Yeah. The bottom one is the explosion. Any other guesses? I kind of like that guess. That's a very good guess. Indeed, that is the explosion. So that is the biggest nuclear test that North Korea carried out in 2017. So our friend here might have identified that the earthquake looks very different to the explosion in that the first part of the wiggle, you compare the relative strength of shaking that was produced. This first part, the P waves are much, much stronger in the explosion compared to in the earthquake case. So that is because the explosion is just a bang. It produces primary waves that are more like sound waves. They just spread out as longitudinal waves, a little bit like sound, whereas S waves that come later are shear waves. They have to have a crack that moves in a relative sense. So the explosion is just an explosion. It doesn't have that shear mechanism. So it does not produce those S waves very efficiently. Okay, so this is how seismology started out. And then people started to realize that they could do a lot more with wiggles. So here's the Earth. This is our current best idea of what the Earth looks like on the inside. Very simplified. So the Earth has a crust, an outer rigid shell. It has a mantle that is solid, not molten. Remember that, because as Earth scientists will get angry at you. And then we've got a core that is the center of the Earth. There's an outer core that's liquid and an inner core that's solid. So how did we arrive at this picture? If we cannot relive the 2003 movie, The Core, where people just went down without melting, apparently, we can't do that, we would melt. So how did we come at this picture? We studied wiggles, and we found patterns in wiggles. So here's a picture that might look slightly small, but this is on purpose. I would just like you to see the big patterns here. So we've got an earthquake up here that happens in Peru. It produces waves that travel through the Earth to stations that are located at different sorts of distances all around. And here we're just collating wiggles from lots of different stations that are at different distances. This is distance on the y-axis, and on the x-axis we have time. So what is happening here? You can trace out the P waves in blue. They're kind of moving out here. You've got reflections of P waves in the red. And then you've got S waves kind of tracing out here, and where you've got the strong surface waves kind of in the tail of the seismograms. So what's also happening here, it's kind of interesting, is that if you follow the P waves down here, they kind of start decreasing in strength. They decrease to the point where they're no longer seen if you go past about 12,000 kilometers away. So something's happening inside the Earth that makes those P waves disappear. So what's happening is that these waves are bending. This is just like physics 101 in action, Snell's law. The velocity inside the Earth that these waves are having changes. The waves are bending. And because the outer core of the Earth, it's liquid, has a lower velocity, waves are bending towards the normal. So they're bending away. So there is a zone where we no longer have P waves, just because of simple bending of waves. Pretty cool, right? Okay, but many people did not believe this. So it took some very, very smart people who had very good eyes to see patterns in very, very few wiggles to discover this. So I'd like to introduce you to one of our science's forgotten people, Inge Lehmann, who was a Danish mathematician. 90 years ago, in 1936, she wrote a paper that had a very simple title. It was called P dash. Very simple title. So Inge Lehmann, here's a picture of Inge Lehmann. She looked at some wiggles, just 3, that were recorded a far way away from some earthquakes. At the time, it was known that the Earth had a core, but they did not know that the Earth had an inner core, an outer and an inner core. So Inge Lehmann looked at these wiggles. She looked at the zone where there should not have been any P waves. And she actually said, wait a minute, there are actually P waves in this zone. What's happening? So she drew some calculations very, very carefully on paper. And she made the case that the Earth probably has an innermost core that is distinct from the outer core, so it's producing some sort of reflection. So many, many years later, we got more data, and Inge Lehmann was proved absolutely correct. And then people with more data, they discovered that the inner core is actually solid. It is a solid ball of metal. So since 1936, when Inge Lehmann wrote her paper, we've come a long way. This is a snapshot from my work. Now we've come to the point where we can model wiggles mathematically by solving the wave equation inside the Earth, wiggle for wiggle. We can match the wiggles individually. This is for an earthquake that happened in Japan. It was recorded about 1,300 kilometers away in China. And here's the black is what was observed. And the colors are what different models that we produced in this study look like. So you can see that in most cases here, of course, the fit is not perfect because a model is never perfect. You have to remember that. But we can fit most of these wiggles to the point where you can't see the observations. We can get very good fit because we can fit the wiggles using state-of-the-art optimization methods. We solve inverse problems to come up with our best possible guess for what is happening inside the Earth, how fast the different waves are traveling inside the Earth. So this is how far we've come in 90 years in seismology in terms of doing models of the interior of the Earth. Okay, so I'm an earthquake seismologist. That means I usually care more about the sources rather than the structure. So that previous slide was more of a means to an end to study sources. But you might be sitting there still asking yourself, what on earth is an earthquake? What is it? So an earthquake, very simply, is the breaking of a fault being a surface of the outer shell of the Earth, the crust, that bounds two blocks of the Earth that are kind of moving independently. A fault is just a break between them. So in a fault, long-range tectonic forces, usually resulting from gravity, will try to force these two blocks to move past each other, whether up or down or sideways. Those blocks will resist that movement by friction, but eventually friction will not be enough, and we will get a break, a very sudden break. That is an earthquake. An earthquake starts at a point, and then it slips or breaks over a surface that we call the fault plane. Okay, all right. Now, earthquakes happen at blade boundaries. I've got this video that I hope will play. Yes, it is playing fantastic. I will just make it play fast so that, and I will just scroll through. You will see lots of earthquakes popping around. We're seeing the Earth from the Pacific here. So you can see lots of earthquakes popping around, but the earthquakes are not everywhere. They happen in very predictable spots. Here, because we're zooming on the Pacific, you might have heard the word Pacific Ring of Fire. The earthquakes are happening all around the Pacific, but not in the middle of the Pacific. So what is happening here? The Pacific is a single tectonic plate. It is moving, it is dancing on the surface of the Earth with respect to the other plates. Here you've got all earthquakes in this period. Big earthquakes, you can see they happen in very predictable spots. And these are the really big earthquakes over magnitude 8. I will explain magnitude in a moment. Okay, so let's go back where we were seeing all earthquakes. All earthquakes. Let's freeze it there so you can see lots of lines are getting drawn, middle of the Atlantic, the coast of the United States, Alaska, Japan. Bit of a mess here near Indonesia and the Philippines, very complex. But the Earth does not like to be simple, remember that. So generally, you can see that most of the earthquakes, with a few exceptions, the Himalayas being an exception, you can ask me about that later because that's a little bit complicated, happen at plate boundaries. So that's because of that thing that I explained just earlier. We've got different plates. The Earth's outer shell is broken into plates. They're trying to move past each other. Where they connect, there are fault planes. So they get stuck. They try to move. Eventually, friction cannot hold them anymore, and we get earthquakes. Okay. All right. So let me just explain what is going on here in California. Here's the state from the Earth. This is from Google Earth. I've just zoomed on the Bay Area. Here is the Bay Area, San Francisco, Berkeley is out there. So here's what's happening here. Yellow line is our plate boundary. It separates two plates, the North American plate to the north, the Pacific plate to the south, down here. And these two plates are moving past each other horizontally, like this. So they move past each other about 5 centimeters a year. That is the speed at which your fingernails grow. So you should not be worried that this motion will get any speed tickets. No. But if you wait a few million years, it is true, some of you might have spotted that already, that LA will come and say hello to us from the side of the ocean. You have to wait a few million years for that to happen, but it will eventually happen. So what is happening here is that these plates are moving past each other. There are forces that are kind of forcing everything to move around. And because there are these forces, the arrow is kind of a spurious arrow, I don't know where it came from, but it forces things to break up into faults. These red lines are all faults that are going up and down the state. We've got the San Andreas fault going all the way down from Mendocino down to LA. We've got the Cascadia subduction zone where the Pacific plate is diving under North America to the north. That goes all the way up to Vancouver Island in Canada. We've got the Mendocino fault gave an earthquake in December 2024 that you might remember as a very exciting day with tsunami warning here in the Bay Area. We've got the Hayward fault that our campus sits on. Last earthquake in 1868. If you want to go see the Hayward fault, just go to the Cal Memorial Stadium. You will see it rip the stadium apart. And then we've got the little sibling of the Hayward fault, the Calaveras. So, and the Rogers Creek fault was going up. It's an extension of the Hayward towards the north. So as I said earlier, these faults are held together by friction. They store energy as they get forced to move. And then that energy can no longer be held, and energy is released in earthquakes. So what earthquakes do is that they cause shaking, what our wiggles are recording. And shaking causes damage, and it is that damage that can cause things to fall and injure people and kill people in some unfortunate cases. So here's an example of what has happened in the Bay Area before. This is the Loma Prieta 1989 earthquake. I don't think anyone in this room was alive then. I was certainly not alive in that earthquake, but this is what happened in 1989, more than 35 years ago now. It was an October morning, so there was an earthquake in the Santa Cruz Mountains, magnitude 6.9. So what had happened is that 63 people died, almost 4,000 people were injured, and if we were to take the damage in today's money, it would be 14 billion. So that's almost as much as my home country produces in a whole year. That was quite a lot of damage. So this earthquake, even though it was not really in the Bay Area, it was like slightly outside, it produced a lot of damage. The east span of the Bay Bridge collapsed, and it had to be replaced with a nice, fancy bridge we have today under very strong shaking, and there was damage in the Marina District in San Francisco as well. So earthquakes, I hope you're convinced, can be pretty damaging, and they are a very good target for both scientific and engineering solutions to be developed. So let's get into the details of earthquakes, starting with earthquake magnitude. So you might have heard these numbers on the news all the time. There's an earthquake. You might hear magnitude 6, magnitude 5 earthquake. What does this mean? So magnitude is nothing else than the size of an earthquake. It is how much energy the earthquake has put into the ground. And what not many people understand is that magnitude is logarithmic. So 1 unit up on the magnitude scale means 32 times more energy put into the ground. So the way to understand this a little bit better is perhaps by the use of spaghetti. We think about earthquakes like bundles of spaghetti. A magnitude 5 might be 1 piece of spaghetti. Magnitude 6 might be 32 pieces of spaghetti. Magnitude 7 will be 1,024 pieces of spaghetti. So this really speaks to the fact that, some people think, oh, if we get lots of small earthquakes on a fault, it will not be able to produce a big one. But when you need 1,024 of these magnitude 5s to match the energy release in the magnitude 7, really, the small earthquakes do not cut it. If a fault is able to give you a big earthquake, it will do so eventually. So here's diving a little bit more into that. Size of an earthquake really matters. So bigger earthquakes really need bigger faults. A fault needs to be big enough to fit that earthquake because we need bigger movement in a bigger earthquake. And bigger earthquakes, because they're bigger, they tend to shake more, and they tend to shake bigger areas strongly. So here is something that might shock people. Here are 3 earthquakes plotted to scale. So this is the magnitude 8.8 earthquake that happened in Russia. This is kind of a map of how much movement was in that fault plane. Darker colors mean more movement. So this fault was 600 kilometers long. To scale, is the biggest earthquake that happened in California in the last 30 years. Big for California standards, but tiny compared to an earthquake 2 magnitude units above. Has to be 1,024 times bigger in terms of the area that it produced. And then we've got the 2014 earthquake in Napa, magnitude 6, caused damage to quite a lot of wineries in Napa, very popular tourist destination here. But how does it compare to this one? It's a dwarf. So this really speaks to the fact that earthquakes follow logarithmic sizes. Okay, so earthquakes have a size. That's how much energy they have to put into the ground. But let me introduce another concept here, the concept of intensity. So earthquakes have one magnitude, but many intensities. So magnitude is really the size of the earthquake. It is how much energy the earthquake puts into the ground. But they have many intensities, intensities being the local description of shaking. Now, shaking intensity is measured on the modified Mercalli intensity scale, or MMI, that goes from 1 to 10. And I know in the room, maybe this will not show up very well. Hopefully on Zoom, people can see it a little bit better. This is a map of shaking intensity in the 1989 Loma Prieta earthquake. Warmer colors indicate stronger shaking. Cooler colors indicate less strong shaking. So you might immediately see is that the warmer colors are more present near the earthquake, the star, and they kind of turn into cooler colors as we go further away. So shaking, as you might expect, goes down with distance away. As how strongly you perceive a light bulb goes away, if you go away from the light bulb, the same happens with seismic intensity. But if distance was the only thing that mattered, we would have seen concentric circles around the earthquake. And that's not what we see. We see kind of an artist's abstract palette all around the earthquake. So what is happening here is that the kind of geology that you're sitting on matters. You sit on soft soils, it tends to shake more than if you're sitting on solid rock. So both of these things matter. So both the local geology and the earthquake itself matter to what the shaking will be at a particular location. Okay, so let me just interrogate this a little bit more. So we see that intensities vary in space quite a lot when we record wiggles in an earthquake. So sometimes this is because of the site. Here's another example from 1989. In Oakland, there was a part of the freeway that was on elevated stilts. It was a raised expressway and it collapsed. So there's 3 colors on this diagram. There's this brownish color in the hills, that's bedrock, solid rock. Where the structure was sitting, it was soft mud. And out here towards West Oakland, more like towards this channel here, Alameda, we had sand and gravel. So you can see the wiggles here. The bedrock was kind of low, shaking, not that big. Soft mud really amplified and it was kind of ringing for a long time. And then sand and gravel kind of intermediate. Even though these sites were, 3 kilometers apart, the character of the wiggle was really, really different. And this really tells you that where you're recording the shaking matters. And where ideally we'd love to be able to record shaking everywhere to record this difference in the site conditions. But sometimes we cannot blame the sites. It's about the earthquake itself. So here's another example from California, lots of stories from our state. The 1992 Landers earthquake near Joshua Tree National Park. I will show you 2 wiggles that were recorded in this earthquake. One at Joshua Tree, this wiggle down here, and one at Lucerne Valley, in the middle of the desert, up here. So immediately these 2 wiggles, you can see they're very, very, very different. The peak amplitude here is about 5 times. And this record here is a lot longer. This kind of finishes earlier. So can anyone hazard a guess as to what happened here? Why is Lucerne Valley, even though it's further away from the earthquake, experience 5 times stronger shaking? And the sites are very different, so we cannot blame the site in this case. Any guesses? This is a bit of a hard one. Yeah. No, it's not about rainfall. I'll take another guess. This is a bit of a hard one. Any guesses from anyone else? Nope.
Does it have to do with like, maybe one, I mean, I don't know the
Mhm.
physics, but, one is more roundness than the other?
Mm-hmm. So that would be a good guess, but I'm telling you that these two sites are exactly the same in terms of their geology. Okay, so the answer here actually has to do with the earthquake itself. You know, I told you that earthquakes start at a point, but they kind of move and break a big surface. So in this case, the earthquake started at that start, but it moved and broke and zipped like a zipper towards Lucerne Valley. So it piled up all its energy in the direction of Lucerne Valley. So it delivered a big punch to Lucerne Valley. It had to deliver the same energy to both Joshua Tree and Lucerne Valley. But out here, the energy was delivered in a punch, in a short and sharp punch that caused this big swing, and then nothing, as in Joshua Tree, because the energy, the earthquake was moving away as it progressed from Joshua Tree. The shaking was kind of protracted, and it never hit very high amplitudes. So this is exactly the conflict that we face when we try to model these things. We always have to ask ourselves, is it the source or is it the structure that caused the form of the wiggles that we see? Okay, so in the big picture, finding patterns in source pattern sites is exactly the long-term question that is asked of seismologists. What kind of shaking will I get over a very, very long period of time where I live or work? So we try to answer this question by building something called a seismic hazard model. So this is the latest version of the US National Seismic Hazard Model. The different colors tell you the chance of having slight or greater damaging earthquake in the next 100 years. So the West Coast is painted in all reds because it's a very high chance of getting damaging earthquakes. The East Coast generally in blues because the chances of getting damaging shaking are not there. There's no big plate boundary in on the East Coast, with the exception of an old plate boundary that was kind of fossilized, and it has the chance of producing earthquakes in New Madrid in the middle of Tennessee. So how we build this model, we kind of have to collect all the possible earthquake scenarios that can affect our location. And then once we have that list of earthquakes, we ask the question, what is the likely shaking from all these earthquakes? So we answer that question using a ground motion model. So that follows the expectations that I explained earlier. If we plot ground shaking intensity on the y-axis, distance away from the earthquake on the x-axis, the shaking falls with distance. The different colors show you magnitude. Bigger magnitude earthquakes have more shaking, but these models are rather generic. They do not really tell us the answer for specific locations. They just tell us if you've got an earthquake so many kilometers away, of this magnitude, on this kind of site, this kind of rock, this is how much shaking you're going to get. But ideally, we want to be able to get specific answers. So can we do better? There's two options here. Option number one, we've gotten good at using very big computers by now, so we can just simulate shaking everywhere. And we're able to do that. The US is a leading power in supercomputing. This is the frontier supercomputer at Oak Ridge National Lab. And they're able to solve the wave equation at very, very fine spatial and temporal intervals to get a picture like this. This is just a snapshot. It's just a moment in time. They're simulating an earthquake on the Hayward Fault, and the different colors show the intensity of shaking. So we are able to do this. Now, this is very useful, especially in cases where you don't have data. But you have to trust that the inputs of your simulation, of your model, are correct. So because we have not seen an earthquake on the Hayward Fault since 1868, there are definitely things we're getting wrong. So one option that more data-oriented people like myself like to go to is get more data. And now in California, we're in the position where we do have a lot more data. So I'll play this movie out here. You will see it progressing from 2015. This is the growth of our seismic network in the past 10 years. So you see as the earthquake, the networks get built out, we're investing in our network. We started out with 400 stations, and we've grown that network in 10 years by 4 times. We're up to over 1,500 stations. So you can see that the entire West Coast is covered in stations, especially the urban areas, Los Angeles, San Francisco Bay Area, Portland, and Seattle. So we have a lot of stations, especially where people live. Now, because we have a lot more data, we can build models like the ground motion model I showed you earlier. I have a lot more statistical confidence. They are more location specific, and they fit the data better, up to 30% better. So that's a very significant impact. Okay, but how do we get all of this new data in California? So the answer to this is a really nice story that I'd like to tell you now in the last few minutes, and that is earthquake early warning. So how many of you have heard of earthquake early warning before? Okay. Did you hear of it because it woke you up in the middle of the night saying, earthquake, 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 drop cover, hold on? Probably. Yes, that was probably last September. I was not here. I was on a plane and I was getting many texts from my friends frantically over plane Wi-Fi. Quite a jarring experience, I have to tell you. But here's what earthquake early warning does. There is an earthquake that happens and we want to characterize it very quickly to be able to tell people before they feel the shaking that they're going to feel shaking that might be damaging to them. So the earthquake happens, it produces waves, P waves that get recorded by stations. So we want to use the information in these P waves that travel very fast to determine where the earthquake was and how big it was so that we can push a message out to people before the slower but stronger S waves get to their location. So how we do this on the West Coast is why we have a system called Shake Alert that detects and characterizes earthquakes very, very quickly over the course of seconds using all those stations that we put into the ground. And the reason that all those stations were put into the ground was to make this system a reality. So this system processes all the data from those stations in real time, very quickly, without human intervention, to push messages out. So once the system determines which area is about to feel shaking, it pushes it out to alerting. We have the MyShake app here, developed here in Berkeley, that delivers these alerts. And once you get an alert, you're supposed to do something. You're supposed to drop cover, hold on, to protect your head because there might be things falling in strong shaking. Okay, so here's MyShake. This is what most of my PhD is about. So MyShake is a smartphone app available for free on Android and iOS. It has been delivering these messages since 2019. Right now, over 1 in 20 people in California have the app, so that's pretty impressive for something that was launched in 2019. And it will alert people for events that are estimated at magnitude 4.5 and above in the areas that are expected to feel weak or stronger shaking. But what MyShake also does, it collects data from users to build a crowdsourced database. So here's how this works. Your smartphones contain an accelerometer. So the accelerometer can determine if your phone is landscape or portrait mode, but it can also record shaking because it is a mini seismometer. It is not as accurate as the seismometers we put into the ground, but it is good enough. So here's an example of a wiggle recorded on a smartphone from a small earthquake in the Bay Area. If you look at this, you would think that probably it's a wiggle from an earthquake. It does not really differ much from what I showed you, other than that it's only 6 seconds long and not 60 minutes, but it's a small earthquake. So if we have lots of smartphones recording shaking out there, we can build a database of thousands of records. And so once you have thousands of records, you can start picking out patterns. So we can start giving details about shaking in our neighborhoods. Here's what we can do with smartphones. Here's an earthquake recorded in Los Angeles in 2020. It was a magnitude 4.5. And I plot lots of triangles. These are traditional stations, and I color them by the shaking that they experienced, whether it was above or below expectations. Red is above, blue is below. And now let's add all the records we got from smartphones. A lot more coverage, a lot more patterns are emerging. There is agreement between the smartphones and the conventional stations, where the stations are red, above expectation, the smartphones are above expectation as well. And then where the stations are blue, below expectations, the smartphones are below expectations as well. So you can have a consistent picture about shaking, but also have more detailed patterns with the smartphones. So remember that these smartphone waveforms are recorded in buildings. They're sitting on bedside tables and office desks. So they contain information about the ground shaking at the ground level, but also information about the building. So our current research is all about pulling out information that can be a dual use product, can be used for both monitoring the health of buildings and also ground shaking. And eventually we want to be able to know how hard is it going to shake over a long period of time on a block by block basis. Okay, so they were only in the infancy of this effort. We're working to find more ways to use smartphone data. Which signals most influence the strength of people, the strength of shaking that people feel? How much of what we see is due to buildings? So for this, we need your help. We need you to download the app, keep it running. Your smartphone might turn off the app, it will send it to the background, so you'll not get alerts anymore and not contribute any citizen science data. So this is for your benefit and the benefit of the research that might end up benefiting you in the future as well. Okay. All right, so earthquake science is a public safety field too. I want to use the last 2 minutes of this talk to just say that earthquake science is a public safety field too. I've kind of shown you that earthquake early warning only came about because we were able to make the case for an investment in a network to deliver alerts. But this all started, so here's just the collage that again proves that earthquake shaking is a real problem. It can cause damage. These are all photos from up and down California, earthquakes that cause damage to the road network, to the infrastructure, to buildings, just as a reminder. So to get early warning, we had to really take the science and go to policy. So this all started, as all science starts, with a big paper, 2003 in Science. This is my advisor, Richard Allen. He was a postdoc at Caltech at the time. He wrote this paper. Papers usually get left on the shelf, even if they're very high impact. But what they did after this was kind of build a case collaboration with other universities, kind of run the system as a test case. By 2014, when 2011 Tohoku happened, they were kind of ready. 2014, they convened the summit. Current governor of California was lieutenant governor at the time, Gavin Newsom. He said, 2014 is not a question of political will. Science is there. Then they got a number of people in Congress to write a letter, including Dianne Feinstein, who was a very senior senator, 2015. 2015, July, Catherine Schultz of the New Yorker wrote a piece that made it all the way to the White House. Apparently it spooked President Obama. It was in the last year of his term, he decided we need to do something about earthquakes in the West Coast. He convened a summit in the White House 2016 that gave $10 million to build out the system in California. And in 2019, MyShake was launched to send alerts to people publicly in California. So this took 16 years to take science to policy, but eventually we got there just because scientists kept bringing the case up to Congress. So here's what my experience is. I went to Congress 2 times in my PhD so far, 2023 and 2025. So I just wanted to give you a little anecdote before we finish. Science policy, taking science to politicians is all about building trust. In 2023, I was a young first-year grad student. That's me out there. And here's a staffer from Senator Padilla's office, the senior senator from California. I went to his office. I talked about my science. I sent him an email after that, and I said, email me if you've got any questions. And that email went unanswered for 6 months. But fast forward 8 months to the next February when congressional budget season was around. I got an email from this person saying, I remember you talked to me about early warning and earthquakes in California. Do you have any input on our current policy process? How much money does the system need for this year? We were kind of shocked that they just gave us a free blank check. How much money do you want this year? But it was only because I was able to go there. I was able to answer questions. Honestly, what we know, what we don't know. And then we built a little bit of trust. So in 2025, I went back. And here's me with the same person. Again, there's a bit of a relationship built there. Again, we've done this process a number of times now. When it's budget season, he emails me. So let's finish up by asking, who can be a seismologist from everything that I've talked about right now? Seismologists need to know wave physics, statistics, data science, geology, classical mechanics, fast code, and know how to communicate. So you might think that only people who are trained or geophysicists can do these things, but I'm here to tell you that if you're a physicist, computer scientist, geologist, an AI expert, or a statistician, you can be a very good seismologist. So if Anything that you've heard today is kind of appealing to you, come talk to us. Remember to download the app for your own benefit, but just to us to close, earthquakes are a fact of life here in California, so seismology matters. Doing seismology here matters. WIGOs can be used to study earthquakes from the hyperlocal to the global scale. And anyone in the physical sciences can do these things. So please talk to us if you're interested. So that's all I have. Right on time. So thank you very much and happy to take any questions. Thank you. All right. Yeah, you got a question.
I don't know, I don't know if you probably heard it before, but like when I was in high school, people kept talking about like, oh, in like a decade or 3 decades, there will be like a big earthquake, and you're like, oh, dude. But
Yeah.
but that like is how, and that kind of brought the question, this is why I was kind of excited for this talk. Cause like, I don't know how you guys like predict time, or how do you guys like predict an earthquake's gonna happen, and how you're gonna predict something to the large magnitude that.
Yeah. So I took that part out of these slides. It was there, but I thought that was a little bit too much to cover in this 45 minutes. But it is a good question. So first of all, for the Zoom people on Zoom, the question was, how can we predict an earthquake? That's a very easy question. We cannot predict an earthquake. Prediction would mean I would be able to tell you there will be an earthquake of this size tomorrow at this time, at this location. We cannot do that. All we can do is give you probabilities, and we do have that. There's an earthquake forecast for a long time period. So we know that in the next 30 years, there's a 2 in 3 chance there will be a magnitude 6.7 or larger earthquake in the Bay Area. We know that because we look at historical patterns. The Hayward Fault gave a big earthquake in 1868. The San Andreas Fault gave a big earthquake in 1906. Lots of other faults in the area have given big earthquakes. So we know that what has happened before, because that energy is building up on these faults continuously, if they gave something in the past, they're able to give it in the future. Now, whether it will be tomorrow, in 10 years' time, or in 30 years' time, I cannot tell you. Your guess is as good as mine. Yeah. But we're trying to refine these numbers. I'm not a statistical seismologist, but funnily enough, these numbers have not changed for 20 years, even though the science has changed a lot in the last 20 years. So we're just working to get more data and more understanding. Those are models, just models. They're maybe an imperfect understanding. So I'm trying to improve things as we go. I hope that answers the question. Yeah. Any more questions from people? Yeah.
You shared a couple really specific examples of how we found out an earthquake moved, but what was in Oakland, I think.
Yeah.
In a more remote location.
Yeah.
I'm sure it depends, but what like density of seismic measuring stations is required to get that specific detail?
Yeah. So that's a good question. So it really depends on what kind of earthquake you're looking at. If you're trying to find out how a very small earthquake moved, a very small earthquake is very high pitched. It's like a high pitched singer. Maybe you think like a small earthquake, like a soprano. You cannot sing the low notes. So those high frequencies will kind of waste away by losses in the crust of the earth. So you need to have sensors very close to it. But if it's a really big earthquake, like the 8.8 in Russia in the summer, you can study it using sensors very far away because it's emitting very low frequencies. It's a base in terms of, you know, the choir of earthquakes. In terms of the density, denser is better. So you're able to get more detail the closer your sensors are. And it's always better if you can cover the entire azimuthal distribution. You have good coverage around the earthquake. So you can really resolve, especially, you know, it's best at minimum to have sensors, you know, at one end, the other end to see, did it go this way? Did it go that way? But also in the cross direction to make sure it did not go in any of these two directions. But always denser is better. Seismologists will always like to complain they don't have enough data. We always need more. We're kind of greedy. Yeah. Any more questions from people? Yeah.
Sorry. So in California, besides small, like, do do you like buy a house based on your research? Like.
Okay, so I think that's a little bit of a sensitive question. I don't want to get sued here. Some seismologists have changed insurance policies based on events that have happened on their own houses. But that is a very personal choice. I can tell you that insurance companies will not write earthquake policies in California anymore because they know that the risk, the exposure that they have is pretty high.
Exposure of what?
So their exposure to earthquake risk. So every time they write an insurance policy, they guarantee that they will pay out for a certain level of damage to your property. Because we have California's population and coverage in buildings has changed quite a lot in the last few years. If you write many policies in a place with lots of risk, you're exposed. So the number crunchers, the accountants the actuaries actually have determined that that risk is too high to take.
So there's politics.
Always, yes.
True for wildfires.
Yeah, also, wildfires, floods, yeah.
There's actually a question.
Yeah.
Andre asks, how do you differentiate from all the other shaking smartphones experience from that earthquake?
Yeah, so that's a good question. So when MyShake was built, it was actually someone's PhD project. So the first thing that they did in that project was to develop one of the earliest machine learning classifiers in seismology that looked at the characteristics of human activity. They actually got students on campus to just dance around and walk. And they also recorded earthquakes, and they kind of found that there was certain features in terms of frequency and amplitude that separated human activity from earthquakes. So they built a classifier that actually runs on the app, is very lightweight, and does that classification. But if I'm being entirely honest with you, that classifier is 10 years old now. So we need to develop a new one that works a lot better. So a lot of when I do my work with MyShake, I look at the waveforms manually. And because I have experience looking at these wiggles, I can tell if it's earthquake or not. Yeah. Yeah.
So what is the most sensitive that you can detect with the smartphone? Or I guess with the net.
Yeah, that is a question we looked at a few years back. So smartphones are always getting better. The accelerometers that the smartphones feature are getting better. So we can record smaller and smaller. We have not found that you can convincingly record earthquakes smaller than magnitude 3 further than 50 kilometers away. So that's pretty limited. But the power of the smartphones is not the single smartphone. It's always that you have a lot of them. So the noise on the smartphones is a lot higher than, conventional sensors. But because you have a lot of them, you can just find patterns from the population, the bulk. Well, that's a good question. Thank you for raising that. Yeah. Any more questions? I think we 5 past, so maybe it's time to let people go. Yeah. Okay. Thank you very much, guys, for listening. Thank you, and have a good weekend.
Yeah.
Thank you very much.